Hello everyone, my name is Thiago. I'm doing a postdoc in Federal University of São Carlos, and today I'll talk about training neural networks in resource-constrained devices. So usually when you want to use a neural network in a resource-constrained device such as Raspberry Pi or Arduino, you have first to train this model. However, training neural networks are very resource intensive, such as you need GPUs, TPUs, or more rich resource devices with cloud or servers. So usually the steps are the following. You have a model with data and you want to train this model with data. You train on a server or in a cloud. Then after training, you deploy this model on your resource constrained device. However, here we propose a novel technique that can train neural networks on the device itself without needing a cloud or servers to train them. First, I'll talk about learning rules of neural networks. So usually when you train a neural network, you employ a global learning rule. The most famous one is the backpropagation algorithm. This algorithm works by calculating the entire state of the network and saving the entire state of the network on the memory. That's why neural networks are memory intensive to train. So you load the first layer into the memory, then you get the second layer and save the state of the memory and so on until the output layer of the network. And after you have the entire state of the network in the memory of the device, you do the backpropagation algorithm that updates the parameters to train the network. Besides using global learning rules, you can use local learning rules. These local learning rules only update the parameters that are shared by both neurons of the network. So for example, here we have a network with 4 neurons, and the second and third neuron share some parameters in common, and you update the parameters of this part of the network by only have information of the second and the third neuron. So we don't need the first and the fourth neuron on the memory to train these networks. Some famous local learning rules are the Hebbian learning rule. That one was the first training rules for neural networks that states that neurons that fire together wire together. But there are also another training rules. For example, besides Hebbian learn rule, there are Ojja's rule and feedback loop. Our proposed technique to train neural networks locally is based on the method called feature alignment. This feature alignment is used to approximate reversibility in neural networks. So this works by you have an input X and you have your neural network, here I call this network E, and you have the output of the X, ZX. Then by using the same neural network, you have a random input R with the same size and shape of X, and you have the output ZR. Then you calculate the distance between ZX and ZR. By minimizing this distance, you get hat R, and you train this network by minimizing the distance between hat R and X. By doing this training, you approximate the reversibility of neural networks. So you can recover the input of the neural network by only having the output information. So this is the inference part. You have the output information ZX. Then you input a random vector. You minimize the distance between both output vectors ZR and ZX with respect to the input vector R. And if the network is optimized well enough, this r hat will be approximated to x. Both will be similar. We can adapt this technique to train networks locally. So we divide the network into parts. For example, you can divide into layers, and you select two layers. You have the activation of the first layer that you chose, XL. Then you get activation from the next layer, XL plus 1. Then you select a random input vector, RL, that has the same shape and size of XL, and you get your output RL plus 1 of the next layer. Then you do the same steps as the feature alignment technique. You minimize the distance between both output layers with respect to the random input layer. So this is shown in these 4 here equations. The first 2 equations is you get the approximation of XL, and the second cost function you use to optimize the parameters. So here you can show that we have the parameters TTL that are shared by both XL and XL plus 1 layers. So by training locally, you can do loading, offloading the layers from the memory. So here are the steps. You first have the input layer, then you get activation of the next layer, the first hidden layer. Then you do the training of the parameters between the first layer and the input layer. Then you unload the first layer from the memory and load the third layer to the memory, calculate the activation function, and update the parameters. Then you unload the first layer, and so on. So you train this network step by step, layer by layer. So you don't need to save the entire state of the network in the memory. You can do by doing small parts of the network and optimizing that. With respect to the spatial complexity of how much memory you need to train the networks both globally and locally, in a MMLP network such as that I showed to you, you need a memory, amount of memory that depends on the number of layers and the density of neurons per layer. While with local training rules, you only need the mean number of neurons per layer. So you only need the average density of neurons in the memory to train. Here we show some results to train neural networks locally. We applied on a regression problem and a classification problem. For a regression problem, we apply to a reconstruction image. So you use here the imnist dataset, which is a dataset that contains handwritten images of digits from 0 to 9. We chose here encoder-only network that has an input layer that receives an image and output some some information of this digit, of this image. The number of neurons here is chosen arbitrarily, so you can choose a different number of neurons in order to reconstruct the network. And we train this network locally, so you do this loading and offloading of the layers to the memory. Here's an animation showing the reconstruction of the images from the last layer. So by using only information from the last layer, you can reconstruct the images up to a precision that depends on the number of latent neurons of the output layer. So from different number of output neurons, we can increase the reconstruction quality of these images. So this graph shows the reconstruction loss with respect to the epochs and the number of output neurons. So 32, 64, and 128 neurons. For the classification, besides needing the latent layer in order to reconstruct the image, we also need a classification layer to classify these digits. So we have a classification neurons and the latent neurons. For MNIST here we chose one hot encoding, so we have 10 classification neurons and an arbitrary number of latent neurons. So for the test set we get the following results. As we increase the number of latent neurons, we decrease the reconstruction loss, and we can also increase the accuracy of the classification. The different colors here show for the network for different number of hidden layers. So we train the networks with 1, 2, and 4 hidden layers. And you can see here as increase the number of latent neurons, we increase the accuracy. In conclusion, we adapted the technique of feature alignment to train neural networks locally, so we can do loading, offloading of small parts of the network from the memory and updating them independently of the entire state of the network. And we demonstrated the feasibility of this technique in real regression and the classification problem of the MNIST dataset. For future scope, we want to improve this approximation of reversibility. There are many ways that we can improve the equation that approximates the reversibility of the neural network, and by improving this we can also get better accuracies or lower reconstruction loss. Here we apply only to MLP networks, but we also can apply to different neural network architectures. For example, we can apply to convolution and transformer networks. We also want to explore different problems and datasets. For example, we want to go beyond computer vision. We want to explore natural language processing. That we want to investigate that if it is possible to train a neural network to do language processing on a resource constrained device. And we want to train neural networks on a real resource constrained device. Very recently we have acquired a Raspberry Pi, so in the near future we will start doing experiments of training neural networks in this kind of resource constrained device. Here is a paper that explores deeper the feature alignment technique, and this paper discuss more about adapting this technique to train neural networks locally. And thank you for your attention.